Hey guys, I'm Ethan with GoBuilda, and today we're going to walk through installing and modifying the Java code for the FTC Starter Robot for the 2024-2025 Into the Deep First Tech Challenge season. Now there are two languages you can use in FTC for programming your robot. You can use Blocks, which is drag and drop and allows you to really quickly get up and running in programming an FTC robot, or you can use Java, which is a more widespread text-based language, which gives you a little bit more control over exactly what your code is doing. In this video, we're going to go over installing and modifying the Java code, but we have another video that will explain the Blocks code for this robot. When programming Java code in FTC, you have two options for how you get that code on the robot. You can either use onBot Java, which is hosted from your control hub and is compiled on the hub. This is nice because it doesn't require any specific programs to be installed on your computer. You just have to go to the IP address of the control hub and use their web interface. Or you can use Android Studio, which is based on your computer and compiles the code there. Android Studio is a more powerful tool and I think is more user-friendly once you have it installed, but it isn't as quick at getting you up and running. We're going to walk through both of these options for programming this robot because our example code is actually the same between onBot Java or Android Studio. Now to start programming for onBot Java, we need to first connect our computer to our control hub's Wi-Fi network. We've already done that, and I'm actually using an external Wi-Fi adapter. This is nice because I can use my laptop's internal Wi-Fi card to connect to the internet, and then have a secondary Wi-Fi card that'll connect just to the control hub. This will let me Google things and download code, pull code from GitHub, all while still being connected wirelessly to the robot. Once we're connected to that Wi-Fi network, we need to go to this IP address. This is static, so it's true for all control hubs once you're connected to their Wi-Fi network, and this gives you some options here at the top. In the Manage page, you can change your Wi-Fi password and look at specifics of your control hub, like the SDK install and the robot controller version, but we're going to pay most attention today to this onBot Java tab. Next, we're going to go grab the Java file that we're going to install on the robot. We're going to go to the FTC Starter Bot resource guide page on GoBuilda.com and scroll to the bottom. Here we have the example code for onBot Java. Now there's also a set of example code for Blocks and for Android Studio Java. Android Studio and the onBot Java file is actually the same, but we install it in a different way. So we're going to grab just the Java file for this installation. This will bring us right to GitHub, and it'll bring us just to that one file that we need to put it on the robot. Now that we're on this page, we're going to click this button with three dots up here in the top right and click the Downloads button. That'll download it onto our computer, and then we can go ahead and upload it to the robot. Now that we have the file downloaded, we're going to go to our robot controller console, find this Upload Files button, and upload that file. Now that we've got the file uploaded to onBot Java, we can hit build and make sure that it functions correctly. There might be an error that pops up here. The most common one I've seen is if you download this file multiple times and it adds a number to the end of the file name, then it might throw an error because the file name doesn't match what it's expecting in the code. So you'll just have to change that file name to get rid of that number that Windows can add on the end of a duplicate file. Now there are a ton of comments everywhere through this code that explains all of what it does. I really encourage you to go through and sit down and really read this front to back because I think it explains a lot of the theory behind what we're going to talk about today. But we're going to dive into the specifics of the code later after we've got this robot up and running. Now the next thing we're going to create is called a configuration file. This is stored on your control hub and you're going to make it through your driver's station, and what it does is associate the motors and servos and sensors that you create in your Java code with specific ports on the control hub. Your code doesn't say, hey, I'm going to plug this motor into port 0 on the control hub. Your configuration file does. Now we're going to go through this example code until we're at about line 146. That's where we start our hardware map. Now our hardware map is where we create the names that the configuration file is going to use, and we need to type those into a new configuration file. On our driver's station, we're going to hit the hamburger menu in the top right and hit Configure Robot. Right now we don't have any configuration files made for any robots on this control hub, so we're going to go ahead and hit New. Now our control hub should pop up here, and if you have additional hubs connected, like an expansion hub to this, it should pop up here as well. But we just have the one control hub because we're only controlling 2 servos and 3 motors. We're going to click the Control Hub portal, click the Control Hub, and click Motors. Here we have our left drive motor connected to port 0, our right drive motor connected to port 1, and our arm motor connected to port 3. We're going to reference our hardware map for the names we use here. So you can see that they're named left underscore front underscore drive and right underscore front underscore drive for the left and right drive motors. And then our arm motor is called left underscore arm. So we're going to go ahead and add these to the configuration file exactly like they're typed in our Java code. So we're going to click this drop down right here that says nothing. Going to click GoBuilda 5202/3/4 series. That's the kind of motors these are. And we're going to enter that name. So the first one is that left underscore front underscore drive. And these are all lowercase. We're going to go to port 1. We're going to select the 5202/3/4 series GoBuilda motor. We're going to go right underscore front underscore drive. Now when you make your own code, you're going to create your own names for these hardware maps. I liked and I added the front to this if you ever want to go and add more drive motors. If you go to something like a Mecanum wheel drive, you might have a left front and a left back motor. So this makes sure you don't need to go rename everything. You can just add a couple of motors to your hardware map and to your configuration file. Then we're going to select the GoBuilda motor again. That's in port number 2, so the third port there. And we're going to call that left underscore arm. Now we're going to click done because that's all the motors we have on this robot. Next we're going to look at servos. Now in our hardware map we have our servos. Now we're going to scroll down in our Java code to where we declare those servos. That's going to be line 177. We call it in our code intake, and we also use that same name in our hardware map. So we have an intake servo and a wrist servo. Now our intake servo, which is this right here, is plugged into port number 1 on our rev hub, and our wrist servo is plugged into port number 3 on our rev hub. Now the way these hubs distribute power for servos has a specific quirk. They have what we call port pairs. So a pair of 2 ports starting with ports 0 and 1, then moving on to 2 and 3, and then 4 and 5. Each of these port pairs shares power. So you have 2 amps that you can share between each of the servos plugged into those port pairs. So we really want to spread out multiple servos if they're going to be working at the same time. If you have something like a claw and it's pinching down on an object and those are on the same port pair, then they only have 2 amps between them, and you can overload the current that you can supply from that port pair. So what the claw will do is it'll close, and then it'll overload that, and it'll open, the servos will turn off, and then close again. And you'll see this like repeating pattern of the servos trying to pull a lot of power, but then both servos together can pull too much power for that set of ports. So we're strategically moving those servos away so that one servo is on the first port pair, and the second servo is on the second port pair. So we have the intake servo is the first servo on this list. Now, the servos that you find here, you'll notice you have 2 options. You have either a continuous rotation servo or just servo. This will need to match what you've used in your code. Intake is a continuous rotation servo. That's how that servo is programmed. So that's what we're going to select here for port number 1. And we're just going to type in intake. Now, port number 3 is our wrist servo. That is not continuous rotation, it's standard. So we're going to just do servo, and we're going to type in wrist. Now we can click done. Done again until we get to save. Now we just need to name this configuration file, and we're going to make a name that we can tie to this robot. So we're going to call it Starter Kit or Starter Robot. Then we're going to go ahead and hit done, OK, and activate. Now that'll enable that configuration file, which will tie the ports that these motors are plugged into to the code that we'll wait for the robot to restart. And when you click the right arrow here, you should see that code file that you just uploaded. You can click on it and click init. Now, if you've done that correctly, you should see something move. You might see an error there. The most common error there is that there's just a typo in your config file. So you can go back through your configuration file and fix that, either by fixing it in the config file, or you can change what it's called in your Java code to match what you added. Now we're going to go ahead and hit the stop button. That's going to let us move around these actuators and everything manually. Next, we're going to go through the process of installing the same file through Android Studio. If you want to skip right to the overview of the code, you can go to this timestamp. The first step to getting this installed in Android Studio is, of course, downloading Android Studio. Now, once you've done that, you should have a page that looks something like this. It'll allow you to click the New Project button, the Open button, or what we're going to click today, Get from VCS. That's Get from Version Control. And this is what we're going to use to pull our example GitHub project into Android Studio. Now, if you already are a team who's using Git in Android Studio, there is a better way to do this, which is to add a new remote and to pull just the new file from that remote. We'll go over that in just a second. But if you haven't used Git before and you haven't used Android Studio before, this is the process I'd recommend. Now, we're in Get from Version Control. We're going to go back to the FTC Starter Kit resource guide. We're going to click FTC Android Studio Java. Now that's going to take us to this page. This is the main page for the repository that holds both the FTC SDK and the one file that we're adding in the Java file. There are two branches here. There's a master and an add starter kit code. We want to make sure we're in this branch. We'll click the code button, and we'll just go ahead and click this button to copy that URL to our clipboard. Now we can go back here, paste that URL, and that should include that branch. And we're going to click directory. Now we're going to decide where to put this in our computer. We can, oftentimes what I'll do is add a new directory, title it something like starter kit code, click OK. That'll make a new folder on your computer, and click clone. Now this will take that repository that we have up in GitHub and just pull it into your computer. It'll create a duplicate, and when we push a new version to that starter kit code, you can pull it into your computer. Now it's working on cloning that repository. We're going to go ahead and hit trust, and that should open this code on our robot. Now we're going to wait while it builds this Gradle, but we're going to give kind of a quick overview for how this is all laid out in Android Studio. We have up here in the top, we have starter kit code. This has made a new project for us that we called starter kit code, and you can find it in that location that you made a new folder in just a second ago on your computer. We can click this next. This is your branch, and this is where you will pull and commit and push. If you get more into GitHub, this will give you more control over your team's version control. Open Java. After that's opened, you should see two folders right here in your starter kit code project. One will be called FTC Robot Controller, and one will be called Team Code. First, we need to switch branches in that remote. So the remote is the repository up in GitHub that you're pulling all this code from. We have the master branch and then the add starter kit code branch. That's what we need. We're going to click this, and we're going to click checkout. This is going to add that code to our computer, and then that'll put it in the team code folder. In the FTC Robot Controller folder, the biggest thing you'll want to be able to look at is external samples. These are a lot of those same samples that you saw earlier in OnBot Java. So if you want to look at something like April tags or ramping your motor speed, you can look at these example files and even copy them into your team code folder. In your team code folder, this is where you're going to put your own code, and this is where we've put the example code for the starter kit robot. Now, you should be able to click this button up here titled Run. It'll push it over to your control hub, and it'll show up here. But first, we're going to look through this code kind of front to back and get some understanding of how it works. Again, I really recommend you read through the comments. They're going to go into more detail than I'll go into right now, but we'll give an overview of how all of this works. Now, we've got our 3 motors and our 2 servos that we talked about earlier, our left and right drive, our arm motor, our intake servo, and our wrist servo. This first variable that we encounter is called arm ticks per degree. Now, our arm motor, we have an encoder plugged in. That encoder feeds back how far the motor has moved since you've clicked the start button on your code. So once you click that init button, that encoder can tell your controller how far the arm has moved. And it does that in ticks. Basically, it sends a pulse every time a certain amount of movement has elapsed. Now, that encoder is before the gearbox, and it's before this external ratio. So there's some math that goes into finding exactly how many ticks of the encoder means 1 degree of the arm. And that's what we're capturing here. So we're saying, if we want to move the arm 1 degree, here's how many ticks of the encoder we need to move. And that turns out to be about 19.7. Once we've calculated that, we have a few different positions here. Now, these are final, meaning they're not meant to be changed through the process of our code. They are for us to reference later on in the code when we want to move the arm to a specific position. So here's a great example, arm collapsed into robot. When we tell the robot to collapse the arm into the robot, then we want it to move to 0 degrees. So that's exactly where it was when you started the code. If the arm is here when you start the code and you tell it to go to 0, it's going to go to here. So it's really important that whenever we hit the init button, we start with the arm in this position right here. And if we want to go to collect something, we want the arm to move 250 degrees. So that's 250 times the arm ticks per degree. And that means that arm is going to move all the way back over here, 250 degrees from where it starts, and all the way down against this end stop. This is where it needs to be when you collect something off of the ground with this intake system. Now, if you make modifications to this robot, it might change where exactly this arm needs to be positioned for different parts in the code. If you say change how the intake system works, you might need to make the arm further up away from the ground when you're intaking, and this is the number you're going to tune there. So instead of moving 250 degrees from where you started, maybe you're only moving 240 degrees. And we're multiplying that by the arm ticks per degree. That way we can think about this in degrees instead of thinking about it as like a couple thousand ticks. That's really not intuitive, and it doesn't make sense for how we tend to do things. And we're going to go through a similar process for things like the intake and the wrist. So our intake, we have a collection speed, which is full speed in one direction, -1. We have our intake turning off, which is 0, and our intake depositing, so spitting back out. And that's going to be at half speed, or 0.5, in the other direction. We have 2 positions for our wrist, either our wrist folding in or our wrist folded out. Now, wrist folding out is in the center of the throw of this servo, so 0.5, and our wrist folding in is 90 degrees from that. The next one we're going to look at is our fudge factor. Our driver will have the ability to apply a subtle change to the position of the arm with the triggers, and that we're going to capture as 15 degrees because we're doing 15 times the arm's ticks per degree. Now we're going to create some variables that we can use to store the position of the arm and the arm fudge factor. These aren't final. These are meant to be changed through the process of the code, and later on we're going to change those variables. These variables here are really around our drivetrain. So we have a left, right inputs, our forward and rotate, and our maximum. Here we're going to talk about our hardware maps, which we talked about a little bit earlier. And in this part of the code, we set the direction of our motors. Because these motors are facing in different directions, we need to have one increase and rotate clockwise, and the other rotate counterclockwise for our robot to drive forward. It's a lot easier to think about this as applying positive power to both motors to make the robot drive forward. So we're going to reverse one of these motors. In this exact application, we're going to reverse the right drive motor. Here we're going to set the 0 power behavior. This makes it so this robot stops much faster. I think it makes it a lot easier to control. And here we set the maximum current. We want the arm motor to be able to output before it throws a flag and tells us about it on the driver's station. Here we're going to set the target position of the arm to 0. That's because we start it at 0. And we're going to set the mode to run to position, and then we're going to call stop and reset encoder. Now run to position is what this arm will use, the run mode it'll use to take advantage of the encoder and to go to a specific position and stop and hold there. Once we ask this arm to drive to a position and stop, it's going to be able to dynamically apply motor power to keep the arm there. It won't just slowly fall like it does right now when we haven't applied power to that motor. That means we can do stuff like hang off of this arm without worrying about the arm back driving and slowly falling down. Here we have the hardware map for our servos, and here we're going to set the starting power for our intake servo, where we're going to start by having it off, and we're going to set the start position for our wrist, which is having it folding in. So because this needs to be folded in to get our set point for our arm correctly, we're going to have that wrist folded in at the start of our OP mode. Then we're going to add our telemetry, saying that the robot is ready, and you're going to wait until you click the start button. Here, this is a section of code that says wait for start. This is where we really go into our code that continuously loops. So past wait for start, in while OP mode is active. This code here is going to continuously run through the entire time that you have the OP mode enabled. The first thing we encounter here is that we're setting these first variables, forward and rotate, to match the gamepad's left stick Y and right stick X. So we're going to push this stick forward and backward to move the robot forward and backward. We're going to push the right stick left and right to rotate the robot left and right. So we're going to assign these values to match what the gamepad is doing. Here we're going to mix these. So our left motor needs to be equal to the forward plus the rotate variables, and our right motor needs to be forward minus the rotate variables. And then here we have, we just set the max and force that you can't try to apply more than 1 or -1 to each of these motors. And then here we just set the power equal to this left variable or this right variable for the left motor and right motor respectively. Here we talk about our intake system, which you can turn on, turn off, and deposit with 3 buttons on the gamepad. Here we have, if you click gamepad A, it'll set the intake power to collect. If you click gamepad X, it'll set the intake power to off. And if you click B, it'll set intake power to deposit. So that means if you click A, it'll try to spin in and intake something. And if you click B, it'll shoot it out. Now we're using if-else statements here, because if you click 2 of these buttons at the same time, we don't want to try to set the servos to like conflicting powers. We just want to use, if you click A and B at the same time, it's only going to set the motor, the intake to collect. As we scroll through, here's the part of the code where we really talk about the arm position. Now, earlier in the code, we made a bunch of different positions that this arm can go to, and here's where we work with those positions. So first we say if gamepad 1's right bumper is clicked, then we're going to set our arm position variable to collect. So what that'll do is it'll move the arm all the way back 250 degrees from where we started. We also set the wrist position to fold it out, and we turn on the intake. This means that our arm will be here and we'll be ready to pick up a specimen or a sample and hold it in the claw. So no matter where the arm was previously, if you click right bumper, it'll move the arm to the intake position, turn on the intake, and fold out the wrist. Now, if you click the left bumper, it isn't going to change the wrist position or the intake position, but it will move the arm to a new position. It'll be about 20 degrees up from that previous one. And as we move through this list, we'll have all very similar functions that'll move the arm to different positions and move the intake and wrist to different positions. Now, all of these are meant to reflect a specific thing the driver is trying to do. When you click right bumper, it's assumed that the driver is trying to intake something. So we're going to move the arm to the position it needs to be in to intake, we're going to turn on the intake, and we're going to fold out the wrist. Now when we click a different button, we're assuming that the driver is trying to do something else. So we're going to make these 3 actuators all follow what the driver is trying to do. We're really trying to say what's the minimum number of buttons the driver has to click to do a main game task. The next one we'll run into is if the user clicks gamepad Y, we're going to move the arm position up so that they can score. Now, we're only moving the arm position because we want to keep a specimen or a sample in our intake until the user wants to spit it out when they click B. As we go through this, we get more niche with what the driver's trying to do. If they click gamepad left, this is going to fold everything back in like where we started. So we're going to fold in the wrist, we're going to turn off the intake, and we're going to move our arm to this position right here. This is if you want to go reset the robot, you just click gamepad left, and it's going to go right back to the starting orientation. If you click gamepad right, this is the orientation you want to be in to score a specimen. So it's going to move the arm out to here, and it's going to keep the wrist folded like this. Or if you pick up a specimen, it's going to lift up the arm and rotate the wrist so that you can hook it onto that bar. If you click the D-pad up, it's going to expect that the user is going to go hang. So if we're going to hang, we can turn off the intake, we can fold up the wrist and make this all nice and compact, and we're going to move the arm straight up and down. Similarly, if you click D-pad down, that's going to winch the robot up, so we're going to go down to about horizontal. Now, each of these correspond with something the user's trying to do, and that's how I really encourage you to think about programming your teleop. You say, hey, instead of giving somebody the ability to move the arm, give them a bunch of individual buttons that they can click that correspond to the action they're trying to do when they're driving the robot. This makes things really smooth and really feel very seamless when you're driving the robot, and you don't have to memorize a ton of different things that each of the buttons and joysticks and triggers on the robot have to do. You just have to say, well, I'm going to go intake, I'm going to click the intake button. They don't have to rotate the arm and then remember to fold out the wrist and then remember to turn on the intake. Here in the code, we're going to look at this fudge factor. Now, we mentioned that earlier. Basically, we're going to create the arm fudge factor by multiplying the amount that we want them to be able to move the arm, so 15 degrees. We're going to multiply that by the right trigger plus the inverse of the left trigger. So the right trigger is going to move the arm up, the left trigger is going to move it down, and depending on how far you pull the trigger, that's going to impact how far the arm is moving up and down. And this is all going to be relative to where the arm is supposed to be. If it's supposed to be straight up and you hold the triggers, then it's going to move the arm slightly forward and slightly backward depending on exactly where the right and left triggers are on the robot. And here's where we actually set that motor's target position. So we go arm motor set target position as the arm position plus that fudge factor. Here we're going to set the maximum speed the motor can run at. When we're running in position control mode, where we're going to a specific position, this is nice because it means it can't go quite so fast. And when we're moving up, that requires a lot of torque out of that motor, which slows it down anyway. Here we check to see if the motor is pulling too much current. This can happen most often if this doesn't get started in quite the correct position and you try to drive it past an end stop. And then we have some other telemetry that just tells you where the arm is trying to go and where the arm currently is. Now that we have a pretty good idea of what our code does, we're going to go ahead and hit build, and we're going to push it to the robot. Now what you should see on your driver's station after you click that and it builds the code on your computer, you should see the robot restart as you've pushed a new version of the app to the robot controller. Now I see on our computer that this is successfully installed, and we should see our driver's station automatically connect back up to our robot controller here in just a second. Now we've got this all set back up, and we have an Android Studio version of that code we installed earlier through on-bot Java. Now, I really encourage you to kind of pick a direction here and say either you're going to use Android Studio or on-bot Java. They're both very viable ways to program your robot, and they have their own strengths and disadvantages, but using one consistently is nicer than trying to mix and match both of those. Now, once we've selected that driver's OP mode, we can hit init, see that init successfully. We're going to go ahead and hit stop first. We're going to unplug our computer. Now, one of the things I like to do for testing code is to put the robot up on blocks. We can use some pieces of U-channel and put these under the robot chassis to move the wheels up off the ground and not let the robot drive around and potentially try to drive off the table. Now, another really reasonable option here is to test robots always on the field, but I do think you get some value out of testing the robot up on a table where you can really quickly stop and hit the power switch if you need to. Now we want to make sure we're clear of any degrees of freedom of this robot, so we know the wheels can spin and we know the arm can spin back, so we're just going to move that through its range and make sure that it's all safe. We're not going to hit anything and we need to stay out of the way of that degree of freedom. So we're going to fold this back in and make sure every time you click this init button that the arm is in this position and the wrist is in this position. That's because when you click the init button, it's going to reset the arm encoder, and all of your positions of your arm are based on that position. Now we can go ahead and hit the initialize button because our arm is reset correctly, and hit play. Now we should have control over all the actuators on the robot. First, we're going to double check our drivetrain. So when we push this left joystick forward, both these motors should drive their wheels forward. So we should push the robot in that direction. When you go backward on the left joystick, it should go backwards. Now, if these are running in opposite directions, make sure that your motor bullet adapter connections aren't reversed. And if they are, just go ahead and make sure they're red to red and black to black. Now, the right joystick here, if you push it to the left, should rotate the right motors forward and the left backward. This will pivot the robot to the left because it's creating that difference in speed between the left and right side. And if you push it to the right, it should run the right motor backward and the left motor forward. Now let's check through our arm positions. The first one is we're going to hit that right bumper. So that should move the arm all the way back over, turn on the intake, and fold out the wrist. And it did all that. So our arm is all the way back. It's a little off the ground because of our blocks. It's turned on the intake, and it's folded out the wrist. And we can go through all those individual positions. If we hit A, should turn on the intake, B should reverse the intake, and X should turn off the intake. So we'll go double check that all of those work. If we click Y, it should move the arm up to a scoring position. If we click up on the D-pad, it should move our arm to a hanging position. If we click down on the D-pad, it should move that to that hung position. So here we're latching onto the bar. Here we are pulling the robot up onto the bar. Clicking left should fold it down back to where we were, and clicking right should fold out with the intake wrist folded in for scoring a specimen. So if you hit intake, it'll fold that wrist out, turn on the intake, and put the arm in position. And then if you click the right joystick, it'll keep that intake in whatever state it was in and fold in the wrist. Now the last feature here we talked about is that fudge factor. So if we go to up on the joystick and we move our right trigger in, we have control over pushing that arm out a little bit. And then if we hold the left joystick in, we can pull it forward toward the robot. Now we can go ahead and hit stop on our code and turn off our robot because we have sent over our code to the control hub through Android Studio or through on.java, Java, created our configuration file, and started to drive around the robot. The next step in your programming journey is to modify this code. This is a great starting place and it works well for this robot, but if your team modifies and adds on to this robot, or you want to change how the driver interacts with the robot, go ahead and make some changes to that code, push new versions, and experiment. This is the fun of programming because you get a lot of control over how the user works with this robot. If you have questions about this or other parts we sell on GoBuilda, make sure to shoot us an email over to tech@gobuilda.com.